we introduce Anywhere3D, a comprehensive benchmark for evaluating multi-level visual grounding in 3D scenes. Our motivation for Anywhere3D stems from everyday scenarios in which humans can accurately align referring expressions with 3D scenes. For example, when instructed to place a floor lamp next to an armchair, humans can visually ground the lamp in the scene by estimating its base diameter and height and imagining its precise alignment with the armchair. Humans naturally perceive, reason about, and localize expressions to anywhere in 3D scenes. However, concurrent 3D vision language models ground free-form referring expressions to precise positions and dimensions in a 3D scene, especially when those expressions refer to regions beyond discrete objects. To further investigate this issue, we propose Anywhere3D, a benchmark with 2,632 referring expression 3D bounding box pairs, categorized into 4 visual grounding levels: area, space, object, and part. To the best of our knowledge, we are the first to propose a 3D visual grounding benchmark that spans multiple levels of grounding granularity, with a particular focus on aligning expressions with 3D locations and sizes at the space level. At each level, we design distinct types of referring expressions to evaluate models' abilities to perceive and reason about various aspects of 3D space. Expressions belonging to area-level tasks typically describe an indoor activity, requiring the model to infer the relevant functional area, which is composed of multiple objects and the spaces between them. Expressions at the space level refer to spatial regions beyond objects in the 3D scene and are categorized into the following 5 types. Size-related tasks require directly adjusting the size of an object. Distance-related tasks involve relocating an object or placing a new object at a specified distance from another. Situation-related tasks require imagining a scenario in a 3D scene from an egocentric perspective. Common sense-related tasks involve common sense knowledge about object sizes, such as a 40-inch TV, or typical spatial locations within a scene, e.g., room corner. Trajectory-related tasks specify the starting point and path of a trajectory, requiring the model to imagine placing an object at the endpoint and to predict its location and size. At the object level, we place particular emphasis on evaluating models' ability to reason quantitatively about object size, shape, and interobject distance. Expressions and part-level tasks refer to specific parts of objects in a 3D scene and can be categorized into 3 types. Movement tasks require models to predict the bounding box of an object part after a specified movement, while relationship and function tasks require models to identify a specific part of an object based on its spatial relationship or function. Here we present the task formulation for Anywhere3D. The model takes as input a 3D scene representation and a referring expression, and outputs the predicted 3D bounding box, represented by its center coordinates and its dimensions along the x, y, and z axes. We evaluate 3 different types of models on our benchmark: LLMs, MLLMs, and 3D visual grounding models. For LLMs, the scene representation consists of a textual scene graph with ground truth object locations, sizes, and VLM-generated captions. For MLMs, we follow the GPT-4 scene setting by incorporating 8 uniformly sampled video frames and a bird's-eye view, in addition to the LLM's textual input, as the scene representation. For 3D visual grounding models, we follow their original input modalities, using point clouds and video images as the scene representation. In general, we use ACC at 0.25 IOU as the evaluation metric. We also construct a human evaluation subset of 200 expressions to assess human performance on Anywhere3D bench. Through a comprehensive evaluation of these 3 types of models, we arrive at the following observations. Human performance substantially surpasses that of the best-performing model, Gemini 2.5 Pro, under the MLM setting, particularly at the space level. Space-level and part-level tasks are the most challenging in Anywhere3D bench. Space-level tasks require more comprehensive spatial reasoning abilities, such as modeling distances and spatial relationships within 3D space, while part-level tasks demand fine-grained perception of object composition. We observe a substantial performance gap between the best-performing 3D visual grounding model, ChatScene, and the best-performing MLM, Gemini 2.5 Pro, across all 4 grounding levels. Specialized 3D visual grounding models demonstrate limited performance, particularly at the space level, as they are restricted to predicting objects within the scene and lack generalizability for multi-level visual grounding tasks. In both the LLM and MLLM settings, models equipped with reasoning capabilities consistently outperform their non-reasoning counterparts. These results highlight the critical role of reasoning abilities in effectively addressing our benchmark. We then conduct a detailed analysis of the two most challenging tasks in Anywhere 3D bench, space level and part level, with respect to expression type within each level. At the space level, we find that trajectory-related tasks are the most challenging, as they require a comprehensive understanding of spatial distance, relationships, and orientation. In part-level tasks, expressions involving dynamic movement present the greatest challenge, with the best-performing model, Gemini 2.5 Pro, achieving only 33.3% accuracy. Models must not only accurately identify the specific part of the object but also understand the object's orientation to correctly predict the position of the bounding box after the movement. To further quantitatively analyze the failure cases of the best-performing model, Gemini 2.5 Pro, we conduct an error analysis on the human evaluation set and categorize the errors into three main types: visual perception errors, logical reasoning errors, and spatial reasoning errors. At the part level, the proportion of perception errors is higher, as this level requires finer-grained visual understanding of object components. In contrast, at the space level, linguistic and spatial reasoning errors are more prevalent due to the increased demand for spatial orientation and logical inference. Here we present qualitative results illustrating three types of errors made by Gemini 2.5 Pro, along with its reasoning process. As shown in the left figure, Gemini 2.5 Pro fails to visually recognize the slanted table in the bird's-eye view image. In the middle figure, the model incorrectly treats the starting position of the trajectory as the geometric center of the bed, rather than the midpoint of the bed's edge, indicating a lack of human-like understanding of such expressions. In the right figure, although the model correctly infers the person's orientation, looking in the negative y direction, it fails to accurately interpret the spatial meaning of right with respect to this orientation. We present qualitative comparisons between the best-performing non-thinking model, GPT 4.1, and the best-performing thinking model, Gemini 2.5 Pro. In this case, while both GPT 4.1 and Gemini 2.5 Pro correctly identify the shelf and estimate the clock's location, GPT 4.1 misinterprets the clock's orientation, incorrectly treating its thickness as its height. In contrast, Gemini 2.5 Pro accurately understands the clock's orientation by reasoning that the thickness would be its dimension perpendicular to the wall, demonstrating stronger spatial reasoning and logical reasoning. In this case, Gemini 2.5 Pro exhibits better situational reasoning by noting that getting up implies the starting point is at the front edge of the toilet, whereas GPT 4.1 simplistically assumes the starting point is at the center of the toilet. Additionally, Gemini 2.5 Pro more accurately reasons about spatial relationships and directions. In general, compared to GPT 4.1, Gemini 2.5 Pro is more effective at leveraging textual and visual information to analyze spatial relationships and situational context. Its reasoning exhibits a greater degree of human-like intelligence. Thanks for your attention. We hope Anywhere 3D will inspire greater interest in beyond-object visual grounding and the advancement of spatial intelligence. For more results, please visit our website or scan the following QR code.